Welcome back, Chemistry 30. So this is the MS2 lab entitled Chemical Compounds Lab. So here we're going to distinguish between ionic and molecular. We may remember that as being covalent compounds based on their physical properties. So you'll be able to look through this preamble here, and that'll enable you to answer the pre-lab questions quite easily, I believe. And don't forget, there are a few more on the top of the next page. Materials, here's an outline of the materials. Basically, we're going to be doing three things here. We're going to be looking at the difference between ionic and covalent compounds by looking at measuring melting point, solubility in water, and conductivity in an aqueous solution. Okay, and all of the material will enable us to do that. So if we start off with what we're doing first, relative melting point, and the key word there is relative. We're not going to be actually measuring melting points, but we'll be relating the melting point of each substance to each other. So we'll obtain a small sample in each compound in a separate well of a well plate. We'll cover a large iron ring with aluminum foil and basically divided it into, now I have 6 spaces here, but we have 7 compounds, so we're going to go A through G actually. Placing a few crystals of each substance in there, and then we're going to place a butane burner underneath. Make sure we have a low flame because we don't want this stuff to catch on fire. We basically just want to heat it up a little bit so that it melts. So I'm just getting the burner ready now, and we're just going to simply write down the order of melting. So of course, whatever melts first, that'll have the lowest melting point, and whatever melts last will have a higher one. And there'll be some substances here that won't melt because we cannot get a high enough temperature with our butane burner. Okay? Then we'll be looking at solubility of water. We'll be putting a few crystals into a well plate. I have done that already, so here it is right here. And we'll be seeing how well these dissolve in an aqueous solution. Then lastly, we'll be using a conductivity apparatus. We have solutions pre-made, and we'll be seeing how conductive it is. So just simply pressing this button tells us that it's working, and we'll look at comparison and conductivity by looking at how much light is lit up. And then, hey, I'll worry about the cleanup here. And so if we look at this page here, so what we may want to do here is our substances. So what we may want to do is just label this A, B, C, D, E, F, G. So label it like that. So sucrose is A, and then sodium sulfate will be in G. So we're going to label a couple things, just what the description is, and then those 3 items that we're going to be testing: melting point, solubility in water, and solution conductivity. So what I'll do is I'll kind of show you what each substance looks like, and you can write it down. So of course some descriptions may be, well, they're all going to be white. But it could be powder, or it could be crystals, or it could be, let's say, spherical, little spheres. Let's see, what else do we have here? Flaky, etc. So those are some descriptions you could possibly use. So the first one, sucrose. Let's take a look at sucrose. So you can take a look. That's what it looks like. Hey, that's a good shot, actually. So sucrose, you could describe that. Sodium chloride, good old table salt, is B. Yeah, that looks pretty good too. Okay. Calcium chloride. It's kind of an interesting one. Okay. Citric acid. Okay. And paraffin wax. There we go. Paraffin wax. Good old acetaminophen. You'll see a red tinge here because the medication had a red candy or a sweet color coatings to make it taste better. So just disregard the red part of it. And lastly, sodium sulfate. Okay, so hopefully you can fit with that. You can fill in the description table there. And then next we'll look at melting point. All right, so here I have all the substances set up. So you can see here, oh, where's my hand? There it is. A, B, C, D, E, F, G. And I'm going to place the burner underneath. I kind of want to turn it down as I have this as high up as I can. I'd like to have this down a little bit because again, I don't want things to catch on fire. I just want things to melt. So we're going to note the order here. Now I'll kind of give a little bit of a hint in terms of which melting first, which melting second, because I know it's somewhat hard to see. All right, so let's put this in and let's see what happens. Okay. So this one, I'm not sure if we can see, but it's definitely melting. E. E is melting. A, you can see it's getting a little brown over there, so it's melting. Well, there we go, there it goes, it's smoking away there. Now this looks like it's melting, but it's not. It's movement from the other substances. And F, we can see some discoloration there. It's definitely melting. Whew, we're getting smoky. So you can write down F and D. D, if we look at D, right there, we could see some melting action there as well. And of course, remembering the identity of A, that makes sense why it's turning that color. C, it's not. C isn't melting. B isn't melting. And the last one, G, it's not melting either. So those ones look like they... C's a little bit discolored, but it's not melting. And D has melted. Kind of a big puddle right here. There we go. So that should be it. That's all we needed to see there. So the order in which things are melting, I think you have it right there. All right, so hopefully you were able to write down the order here. You can put 1, 2, 3, 4 to the 4 substances that melted in order, and then the other ones just simply N, no melting. Now look at solubility. So it'll either be soluble, which means dissolves, or not soluble, which does not dissolve. All right, so I have it under the same scheme here. So A, B, C, D, E, F, G. So A, B, C, D, E, F, G. So what I'm going to do is I'm going to add about 10 drops of water to each. So you can see the relative amounts of, I try to get equal amounts of everything. So we're going to be looking for is to see, does some of this disappear? And of course it's not disappearing, it's just simply dissolving. So it's breaking down into solution. But for our human eyeballs, to us it looks like it disappears. Okay, so I'll kind of fill that up. So take note of what happens here. So we have what we had originally there. Now, do you see, does it appear to be disappearing? I'm not going to say either way. I'll leave it up to you to decide whether you think it's disappearing a bit. So remember how much we had originally. Had about that much. Take a look at what's going on now. Okay, so here's the first one. Second one. Let's see what's going on here. Just give it a little mix with the toothpick here to see if we can dissolve. And take a look. So is there less than what was there originally? Is there less? Again, I have about the same amount here as there was originally. Okay, substance C. All right, so look at what's there now. And I'll give it a little mix. Oops, one jumped out of here. mix this, get rid of the one from here. So you're thinking, oh, of course you have less because one jumped. Oh, look at that. Look at that. Look at what we have left. Of one big chunk there. So that kind of gives you an idea. Substance D. Substance D. What do you think? That should be good enough. Look at that. Substance E. Okay, so look at what we have. I'll mix it. Ooh, look at that. Floated to the top immediately. Is it dissolving? Mix, 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 mix. Interesting. That's what we got there. Trying so hard not to let you have any hints. F. All right, looks like a mess. So mix, mix, mix. What do you think? What do you think? And the last one, substance G. Give that one a mix. So compared to what there was originally, what is there now? All right, so we should be able to label that chart. And then the last thing we'll do is conductivity. All right, so the last one, conductivity. We'll take a look at what happens here with the conductivity apparatus. So I'm going to grab what I was using there was water. It's distilled water, which means all of the particles have been taken out of it. So let's see what it reads. Hopefully we can see it here. So hands in the way. Press this, okay, so it's working, and I want to see. Okay, so you can see, oh, we can't see it, darn it. Here we go, let's use this hand. There we go. So you can see one red light. See it there? So one red light. So distilled water, distilled H2O, one light. Because I know there isn't anything dissolved in that. So that'll kind of give us an idea of what something that's non-conductive should look like. Then over here, looking at what distilled water does. So right there, see that number 1? Okay, tap water. It apparently has, oh, it kind of jumped to 2 but went back to 1. So we'll just go with that. We'll go with 1. So maybe the tap water sample I picked didn't have, okay, see, 1 light again. Okay, so we'll go with that. So non-conductive is 1 light. All right, so let's look at, so I have these in order again, A through G. So I have sucrose here to start off with. And I dissolved each of these in distilled water. So if it's non-conductive, it should have 1 light. Okay, so what do we got going on here? Try to get that into the water. Geez, we don't even have 1 light there. So that's definitely non-conductive. Okay, sodium chloride. Sodium chloride's the next one. Okay, so hopefully we can see that 1 light there. There we go. I gotta just orientate my hand here right. All right. Oh, we got 2 lights. 2 lights. So we can definitely say that's conductive. So what you could do is say one light, non-conductive. Here we can say two lights, and that will mean conductive. Okay, so we'll keep going through the list. Next we have calcium chloride. Calcium chloride. Let's see what this one does. All right, so try to get that in. Oops, I'm pressing the wrong button. I pressed high. I bet I did that with the tap water too. I pressed the wrong button. So here, oh, it's hard to get my finger out of the way. There we go. Oh, look at that. Oh, my finger's just in the way there. There we go. We can see two lights. Two lights. Now I wonder if I go back to the tap water, because I think I was pressing, I'll have to go back in the video and see, but I bet you I was pressing the wrong button. I was pressing the high as opposed to the low. Let's see here. Tap water, yes, see tap water, two lights. There we go, now we're making sense. Tap water is two lights, indicating dissolved substances. Citric acid is the next one. Let's make sure my thing is still working here, so pressing, yeah, nothing happens. All right, so press the low button. Again, try to orientate my hand so you can actually see. Two buttons, or two lights, I mean, two buttons. Two lights. Okay. Next, paraffin wax. Good old paraffin wax. Maybe some of you make candles and use it. All right, let's see if I can get this in. Oh, one light. It's weird because I thought I was two there for a second, but nope, went back to one. Acetaminophen, you can see that red dye kind of changed the color on this a little bit. All right, looks like one light for acetaminophen. And the last one, sodium sulfate. Sodium sulfate. So we'll put that in, and oop, slipped there. Two lights there. There we go. There we go again. So I think we have everything done there. So we have everything on that table. In terms of writing up, group the compounds into two groups according to their properties. List properties of each group. So I'd pick one property. Most people like to pick this one because you can easily see you have the high melters, the high melting point, the ones that didn't melt, versus the ones that did melt, which would be low melting points. So you could label it like that, write down what was low melting points, the ones that you actually got numbers for, and high melting points, ones that weren't able to melt. And then within these groups, see if you see any patterns with solubility and conductivity, okay? So once you have your low, can you further organize it so that you have soluble versus non-soluble, or conductive versus conductive, okay? It's a little tricky to do, but see if you can arrange it to see if there's any other pattern that you see. And then when you're done that, the next question, number 2 on the next page, says, so all of the ones in the same group, so let's say all the low melting ones, do they all have the same properties in terms of soluble and conductivity? So that's what you're going to do that, and then give an example from the experiment. Over here, all of our substances, I'm going to get you to write the chemical formula. If you forgot how to do some of them, or for example, paraffin wax, it's a tricky one. It has a generic name using C's and H's, and they use a letter. You can Google that and see what the formula is, and then is it ionic or covalent? So if you're not sure, again, you can Google that to see what it is. Okay? And then the last page, write a few sentences to describe the properties of ionic compounds, and then discuss the molecular ones, or actually what we mean by that are the covalent ones. So make sure you talk about the physical state of each one. Hint, hint, I think everything we used was solid today. So you could talk about white, the color, what it looked like, and what that was in. Melting point, did we have low melting points or high melting points for ionic and covalent? Conductivity, was it, for the most part, were they conductive or non-conductive, if you can tell? If you can't tell, just write down what the majority had. And then soluble versus non-soluble, what did you have? So all 4 of these points you need to make for ionic and covalent. All right? And then the last one here, properties of compounds depend upon the strength of their attractive forces between particles. The particles that make up ionic compounds, or ions, are held together by ionic bonds. Things that are molecular are held together by intermolecular forces. So which are stronger bonds, molecular or intermolecular? And then a huge hint of which one would be held tightly, which one has the higher melting point. So hint, hint, if it didn't melt, that means it's held really tightly, and we have a hard time separating it from solid into liquid. All right, so that's the lab, folks. So you should be able to do that. Go back and look at the observations if you need to. And of course, if you have any questions, don't be afraid to ask. All right, we'll see you again.